Now, the next section we'll look at that will be very quickly is just the independence of complements. And we'll go through a relatively quick proof here, but the ultimate way to look at this is starting out with our definition of independence. And the definition of independence, we said, is that the probability of A intersected with B is equal to the probability of A times the probability of B. Now, our intuitive argument here is that if we have two events, and we'll call them A and B, and we look at this graphically, we can say ultimately that the area that is represented by A intersected with B is just this middle section here. And then the probability of A is going to be this entire red area here, and the probability of B is this entire area here. But if we look at that with respect to our sample space, we can also say a little bit differently that A is equal to A intersected with B unioned with A intersected with B complement, or more accurately stated, B prime, our complement of B. So from this, we can ultimately go into a formal proof and say that the probability of A is equal to the probability of A intersect B plus the probability of A intersected with B complement. That part hopefully makes sense based on what we just derived above from our sets. Now, the next piece of this is to say that that is equal to, again, from the probability of A intersected with B, we say that the probability of A is now equal to the probability of A, again, assuming these events are independent to begin with, A and B. This is the probability of A times the probability of B, and we get that by plugging it into our equation for independence. And then we can add on again the probability of A intersected with B complement. Now, if we go through and look at this a little bit differently, we can rearrange some terms and say that the probability of A intersected with B complement, we're looking at this term over here, is equal now to the probability of A minus the probability of A times the probability of B. And you may look at this and say, okay, factor out the probability of A. So we now have that the probability of A intersected with B complement is equal to the probability of A times 1 minus the probability of B. Now, the question I would ask is, what is the 1 minus the probability of B? Well, we said earlier in our first lecture on probability that our sample space, omega, is equal to 1. And that B complement is everything that is not B, which means that 1 minus the probability of B is really just saying that it's the probability of B complement. And to write that down formally, we can say that the probability of B complement is equal to 1 minus the probability of B. And intuitively, this should make sense. Now, with that information, we can then take this equation down here that we just ended with and write that the probability of A intersected with B complement is equal to the probability of A times the probability of B complement, just substituting in this equation, which holds because, as you may recall, we started here with the probability of A, and based on this, we can show that even the complements still hold with this same equation. But more importantly is that since we started with the definition of regular independence and moved that into the independence of complements, that if two events are independent, then so are their complements.